In this video, we're going to be talking about the Gauss-Markov theorem. So we're going to be continuing our discussion on the Gauss-Markov theorem. Again, as I have reiterated before, what you need for the Gauss-Markov theorem is the acronym BLUE. So we have covered linearity and we've covered unbiasedness. And in this video, we're going to start, our discussion on something called efficiency. Now, efficiency has got to do with the second moment of the error term. So second moment of the residual, which is variance of ui, which is equal to variance of ui given xi, which is equal to sigma squared. So this was your assumption of homoscedasticity, which has been covered earlier, right? So under homoscedasticity, you are saying that given the value of xi, the variance in ui is going to be constant across xi's, and that is going to be equal to sigma squared, right? Okay, so given that you have this assumption on the error term, efficiency requires, or efficiency of the parameter requires you to talk about the variance of the parameter itself. What that means is that when I say variance of the parameter, what I mean is that how much is the parameter differing from the estimator, right? So the variance of the estimator is going to be, or the variance of the estimate is going to be, a measure of how much does this value of the estimator differ from my true value or from my population parameter, which I'm trying to estimate, right? Okay, so that's the idea of efficiency here. How do we get to it? Well, we start by calculating the variance. Abhi to hame variance pata hi nahi hai, right? So first we will calculate the variance, then we will see how the OLS variance is the minimizer in the class of estimators which are linear and unbiased. All right, so let's start with B2 once again. Now you know that B2 is nothing but summation I xi minus x bar into yi minus y bar over summation I xi minus x bar squared. So again, I can write this as summation I xi minus x bar yi over summation I xi minus x bar squared. This is going to be equal to summation I xi minus x bar into beta 1 plus beta 2 xi plus ui. Like I said earlier also, the first thing you do is substitute what you know into what you do not know. Summation I xi minus x bar squared, right? Okay, so I can write this then as summation I xi minus x bar into, this is beta 1 summation I xi minus x bar plus beta 2 summation I xi minus x bar into xi plus summation I xi minus x bar ui, right, over summation I xi minus x bar whole square, right? Okay, so you know that this term becomes 0, right? What you're left with, and this can get cancelled, so what you're left with again is beta 2 plus summation I xi minus x bar ui over summation I xi minus x bar squared, right? Okay, so let's look at this expression a little carefully. Let me just switch colors here for a second. Okay, so B2 you have seen is equal to beta 2 plus summation I xi minus x bar ui over summation I xi minus x bar squared, right? Okay, so since this is in fact variance of, so if I say variance of B2 equals variance of beta 2 plus variance of this entire term, this is going to be equal to 0, right, because it's a constant, and what you're left with is this particular term here and the variance of this term. Now again, please do not get confused. When I say that the variance of beta 2 is 0, I'm saying this because beta 2 is the population parameter. What you're in fact calculating in this entire exercise is the variance of B2, which is the sample estimate. Okay, please do not confuse the two. It will make your life very miserable if you do that. So variance of beta 2 is going to be equal to 0 because it's a population parameter and it's a constant. Okay, now variance of this entire term right here, the first thing that you should know is that variance of a times, let's say where a is any constant, variance of a times any random variable, right, is a square variance of that random variable, right? So that's one. The second thing is that variance of y plus z is simply variance of y plus variance of z plus 2 times covariance of y comma z, right? So 2 covariance yz. All right. So these are the two rules you should kind of keep in mind when you're working these things out. Okay, so let's just try to look at this term here. So what you have is variance of summation xi minus x bar uy over summation xi minus x bar square, right? Now both these things are constant. So first of all, let me take this one out. So denominator to I will take out directly, right? So I will just take this out and I will say, okay, 1 over denominator squared variance of summation I xi minus x bar ui. This again, because this is a constant, I can in fact take this also out and I can say, okay, 1 over denominator squared summation I xi minus x bar squared, right? And then I will say ui. I'm sorry, let me just correct this error here. I actually will not take it out right now because I cannot, simply because there is a summation sitting right here. So because of this summation that is sitting right here, I cannot take this out at the moment. What I can, however, do is take the variance operator sort of inside, and then I can say that summation I. So in fact, I should write this out in 2 steps. Hold on. Eraser. Okay. Right. So I should in fact write this out, like I said, in 2 steps, which is going to be equal to summation I variance of xi minus x bar ui, right? So which is going to be equal to 1 over denominator squared summation I xi minus x bar squared, because this is simply a constant. Remember that your x's are non-stochastic. X's are given. X is your data, right? This is your sample. This is your data. You have this. There is no uncertainty. There is no variance associated with the data at the moment. In the sense that, let me rephrase that. What I'm saying is that given that x's are non-stochastic, given that they are in fact not random variables, the variance of any constant is going to be simply 0, right? And in the case that you're taking the variance of that constant multiplied with another random variable, you will have to take this constant out as a square and then calculate the random variable's variance, right? So that's all I've done here. I have just taken xi minus x bar squared outside and said, okay, this will be then variance of ui. Notice that in this entire process, I've not touched the summation as of now. This is very, very, very important. Please do not mess up the order of these, order of the way you do these things, because you can end up making a mathematical error, or worse, you will not be able to get to your answer. So be very careful. I will suggest kind of looking over this video, doing this at least one time at right after you watch the video, and then kind of progressively doing it once or twice more before your final exam. Okay. So given that you have this now, I have just said, okay, 1 over denominator squared summation I xi minus x bar squared. Now variance of ui, as you know and you've assumed, is homoscedasticity or homoscedastic errors. So this is going to be equal to sigma squared. Now because sigma squared is a constant in this summation, this in fact can come out, right? Because it's just a constant, right? So I will then say, okay, 1 over denominator squared, sigma squared, summation I xi minus x bar squared. Recall that your denominator is nothing but actually this term squared, right? So this one term will get cancelled. So essentially this is summation I xi minus x bar squared, right? And sigma squared summation I xi minus x bar squared. So this term will get cancelled, right? And what you're left with is simply variance of B2 equals sigma squared over summation I xi minus x bar squared. And that's your variance of B2. So I know this has been a long journey of calculating the variance, but if you go over it, step by step, I think you'll be able to follow. I will again say this, in your books there is a slightly different way of calculating these things which has been followed. I personally disagree with that method. I don't think that there is any need for us to complicate things further when we're already dealing with so much of terminology. So I'm going to stick with these methods. Of course, if you have doubts in any of the books methods, please feel free to reach out. Before I kind of close on this video, I'm also going to talk about the variance of the other parameter, which is b1, or sorry, rather the sample estimate of the other parameter, which is small b1. And yeah, that would be it for this video. So let's just look at that very, very quickly. Let me switch colors here again because I can't see this color. So okay, you have B1 now. Oh my god, did I call that B1 accidentally? No. Okay. So B1 is y bar minus B2 x bar. Variance of B1 is going to be equal to variance of y bar minus B2 x bar, which is equal to, well, variance of y bar is nothing but 0, because it's, like I said, it's data, it's given, it's a constant. So 0 minus b2, so x bar variance of b2, and this will be x bar squared, because again you have a constant times a variable, constant comes out squared. X bar squared variance of b2, so this is x bar squared summation sigma squared over summation I xi minus x bar squared. You can check these against the expressions given in your books or your notes, whatever. The expressions will not be different. Just the way that we've calculated them is mildly different, right? Okay, so in next video I'm going to kind of talk about I'm going to kind of reiterate these formulas and talk about a few other things related to them. That's it for this video. I will again say this for one last time. Please work these things out yourself. It doesn't matter if you see it on the screen. Until you do it yourself, you will not know where you will get stuck. So thank you.